today is Alexander Schmitt from the Freie University in Berlin, Germany. And he's going to talk on general coherent systems. So please, Alexander.
Yeah, thank you. Good morning. So it is a great pleasure and honor to be here at IMPA. And I would like to thank the organizers, in particular Eduardo and Marcos, who is unfortunately not here, for making this possible. So in my talk, I will work over the complex numbers, and X will be a smooth projective, connected projective curve. And so since this is a pretty broad meeting, I will try to provide some background on the different objects which are relevant. So the start of the history is classical. So you remember if you want to give a rational map from the curve X into some projective R space, then this is the same to giving a line bundle L on X and a linear subspace of the space of global sections of L of dimension R plus 1. And classically, this is called GRD. So this is why I stick to this notation, where D is the degree of the line bundle. Right, so you study the projective geometry of X in terms of line bundles and their global sections. And then, of course, you can ask many basic questions. For example, for which values of R and D do you have a GRD, a base point free GRD on the curve X? Or you can also vary X and ask, for example, for which values of G, R, and D is there a curve of genus G embedded as a curve into projective space of degree D. So this is, for example, discussed in chapter 4 in Hartshorne, introduction to this. And these questions and many others, as we have seen yesterday, are part of the classical topic of Brill-Noether theory. And of course, this is exposed from the modern viewpoint in the classical book by Abarello, Canolba, and Griffiths-Harris. So yeah, there you find all the basic statement in this circle of problems. And now you can try to look at natural generalizations of this. So I define a Brill-Noether pair, or more frequently it's called coherent system. So is a pair E, comma B, where E is a vector bundle on X. Now it is allowed to have any rank, and V is just a linear subspace. Right. So it's natural generalization of what we find in the classical theory. And now you have a discrete invariant, which is could be called type. And here R will be the rank of E. D is the degree of E. And S is the dimension of V. So letters have slightly different meaning from before, but that GRD is just very classical. So I use this. But now you have a basic problem. So unlike the rank 1 case, so if R is at least 2, so if you want to study the classification of these type of objects, it's just natural to fix these discrete invariants. So these two classify the vector bundle as a topological bundle, and of course, dimension is also sensible to fix this. So if R is at least 2, then there is no scheme of finite type. So just variety over C, which parameterizes all coherent systems of type RDS up to isomorphy. So this has a precise meaning. So you want that on the scheme times the curve, you have a family of such coherent systems, such that for any coherent system, you find a point in the scheme, such that the restriction of the family to that point times X is isomorphic to the coherent system you are looking at. And this fails because you can always, in rank 2, just take copies, direct sums of two line bundles. So, you can just make the degree of L1 whatever you want, and then you choose the degree of L2 appropriate. So this means if you want to study the classification of these objects, then unlike the classical case, you have no nice parameter scheme to start with. And so you can try to overcome this in distinct ways. So you can either use a theory of stacks, which has been done, but not to great extent in this setting of coherent systems, especially, particularly because you have such degenerate objects. Or you have to restrict the class of objects you are looking at and study only this particular class. And this is done by a kind of stability condition, but now in the classical sense. So it will depend on a positive rational number, and then the alpha slope of a coherent system, let me call it for a moment G comma W, is mu alpha of G comma W, which is, if G is non-trivial, the degree of G plus alpha times the dimension of W divided by the rank of E. So in principle, you are allowed to take W to be the zero vector space, so then you get just the classical slope of a vector bundle. G is a vector bundle, so this is a coherent system. So G is a vector bundle and W. No, I call it G because I will apply it to distinct things. Yeah. So. Oh, there, sorry, here, you mean. Oh, sorry, yeah, here. Yeah, here it's G. Thank you. Right. Okay, and now you say that such a coherent system is alpha semistable. So alpha semistable or alpha stable, so there will be two notions. So if for all subbundles, which are non-zero and not everything, the alpha slope of f, and you take the intersection of v with the global sections of f, then this should be bounded by the slope of EV. So I apply the slope to these two coherent systems. So this notation means if you would like to define alpha semistable, you use less than or equal to. And if you want to define alpha stable, you use the strict inequality. Okay, and then there is work of many people, and most well known is the work of Le Potier and King and Newstead. So you get moduli spaces. Alpha stable of, for the given type, which is contained in the moduli space of alpha semistable as an open subset. So these here are the alpha stable ones. And these here are the alpha semistable ones. And this here, this is important, is projective. Good. So, I mean, the reason is if you look at the stable objects, you get this quasi-projective moduli space, and its points are in natural correspondence to the isomorphic classes of alpha stable coherent systems of type RDS. Sorry. And this space has a natural compactification by alpha semistable objects, but there's a little price to pay. In the boundary, you have a coarser equivalence relation than just isomorphy, so you have in the boundary some identifications which are not natural, but which cannot be avoided, and the bonus is you get some projective moduli space. But if you look at the condition, you see that under some coprimality conditions on RD and alpha, semistable will be equivalent to stable, and then you get a nice projective moduli space. Good, and let me at least indicate some motivation, except for natural curiosity, why these moduli spaces are relevant. So, as I pointed out, if you take S equal to 0, then you just get classical semi-stability for vector bundles, and you get the moduli space of semi-stable vector bundles, which is one of the most important and interesting moduli spaces in algebraic geometry. So if alpha is close to 0, then there is a morphism from the moduli space of alpha semi-stable pairs and coherent systems to the moduli space of semi-stable vector bundles of degree of rank R and degree D. Good, and oops, in this way you get as image interesting loci in the moduli space of semi-stable vector bundles. For example, some kind of theta divisor. And another classical, but I think frequently used construction is following. If you have a coherent system, then V is the space of global sections of E. So you can look at the evaluation of global sections on E. So if this is generically surjective, then it defines a rational map. Phi from X to the Grassmannian of R-dimensional quotients of V. So morphisms, in particular morphisms from X to Grassmannians are described by coherent systems, so they also have some applications to the projective geometry of the curve. Good. The basic problems in the setting of Bernoulli moduli spaces of coherent systems, like when is this moduli space non-empty, when is it irreducible, when is it connected, and so on. These questions have not been settled in full generality, just some particular ranges. And also the answers are different from the classical Brill-Noether theory, where R is equal to 1. So there's, for example, a recent survey by Peter Newstead on open questions in this direction. Good, and a final class of objects which are related to what I would like to talk about are the decorated vector bundles. So you fix some R and a representation. So a representation of GLR on the finite dimensional C vector space A. So just a homomorphism of algebraic groups, or equivalently a linear action of GLR on this vector space A. So then you may associate with any vector bundle of rank R. So with any vector bundle E of rank R on X, we may associate now a vector bundle E index rho with typical fiber A. So the most elementary way to see this is you just choose a local trivialization of E. Then E is defined in terms of a co-cycle with values in GLR. And then you just transport this co-cycle from GLR to GLA and glue together E rho with this new co-cycle. So examples are tensor products or endomorphism bundles and so on. Good, and now a row pair, which is has been studied for many examples, is now A comma sigma with E, a vector bundle of rank R on X, and sigma is now, I just also need for a line bundle on X. Sigma is a section of E rho tensor L. Okay, so to get an idea, let me give you an example. So if you take rho to be the adjoint representation, so the action of GLR on the space of R by R matrices by conjugation, and L to be the canonical bundle, the canonical line bundle, so the bundle of one forms, then you get E together with a section of the endomorphism bundle twisted by omega, so you can also write this as an endomorphism from E to E tensor omega, and this is called a Higgs bundle. And it's probably the most famous example falling into this category. Section, yeah, sorry. No. Yeah, okay, if it is also as rank 0 bundle, it's also, yeah. Right.
So in this case, E rho is just E tensor E.
Yeah, or end of E. Yes. End of E, which is isomorphic to E dual tensor E, exactly. And again, if you would like to study the classification, you take a rational number, positive rational number, and you get something which is called delta semi-stability or stability. I will not write it down completely. I will just say that the test objects are weighted filtrations of E. So these consist of a filtration of E by subbundles. So S is not fixed. So the ranks may jump by more than one. It doesn't have to be a complete filtration. And alpha, so this is the filtration, and alpha is just a tuple of positive rational numbers. Well, so you should see this in analogy to classical geometric invariant theory. So if you look at the action of GLR on A, given by this representation, you get some notion of semi-stability, and you test it with the Hilbert-Mumford criterion, which involves one-parameter subgroups of GLR. And any one-parameter subgroup gives rise to such a weighted filtration. This is the essential datum you need to compute this Mumford mu. So, and I will just mention two things. So I will need one quantity defined in terms of such a weighted filtration. So this is the sum from 1 to S, alpha I, degree of E, times rank of EI, minus degree of EI times rank of E. So if you have paid attention very carefully, you will recognize something like the difference of slopes, just multiplied by rank of EI times rank of E. So this is related to this slope inequality. And the second thing is that, which will be important, is this induces a weighted filtration F dot beta dot of E rho, which might be longer than our original filtration. So as an example, I take A to be the second symmetric power of, say, the dual space of CR. Let's just take C2. So space of binary quadratic forms. So now if you have E and a line subbundle, so you don't have much space for your filtrations, then you just form this filtration, and then you can just take alpha to be 1. But then if you look at the induced filtration of the second symmetric power of E dual, so I will just indicate this very schematically. You get something like this. So these are all forms for which n is in the radical. And these are all forms locally for which n is isotropic. So this, since you are dealing with symmetric matrices, this is rank 1, this is rank 2, and this is rank 3. And so the corresponding one-parameter subgroup, so it would be actually of SL2. So Z goes to Z to the minus 1. And then you compose it. Yeah, I will not write it down, but then because I take the dual, you get these. So here you have the weight -2, because here you have only -2. Off diagonal, you have weight 0. So here, weight 0, and then here, the biggest weight which occurs is weight 2. So the differences in weights are 2. And then one also divides by the rank. So beta 1 equal beta 2 equal 2/3. So this would be the induced weighted filtration. Okay, so now I can finally tell you about the general coherent systems. By the way, in the afternoon, I think in the talk by Dapeng Mu, you will get some illustration how such moduli spaces work, at least an analogous example on surfaces, so which illustrate variation with the stability parameter and so on. So okay, so I fix rho as before. And the line bundle as before. And now I say that coherent row system is a pair E, comma V with E a vector bundle of rank R on X. So R is fixed because I'm looking at the representation of GLR, and V inside the global sections of E rho tensor L is a linear subspace. Good. So let me give 2 examples. The first one is as before. Rho is the adjoint representation. L is the canonical line bundle. And then so you have E, and now V is a subspace of NE tensor omega. So this is a coherent Higgs system. And this was proposed by Brambilla Paz. Garcia Prada, and Goten. You can find some talks by Letizia online discussing this, and so they have some particular applications of this kind of objects to moduli spaces of Higgs bundles in mind. And another interesting example which I find promising, at least in principle. So building on what I said before, so you take the representations of G on the space of homogeneous forms of degree D. And now you note that, well, I can write it like this. So such a homomorphism from the second exterior power, this symmetric power of E to L, this corresponds to a certain divisor inside the projective bundle. So the classical projectivization, so the projective bundle of lines in E. So projective bundle of lines. So this is phi but over X. And then you get an induced fibration or map to X. So, so if phi is non-zero, it will be generically surjective. At points where it is not surjective, you will have just the whole projective space as a fiber, so this might be reducible. And so generically, the fibers of D are hypersurfaces of degree D in the fibers of E, of P of E. Which are isomorphic to. So it's a nice geometric object which is fibered over the curve, say in hypersurfaces of a certain degree. And then a coherent system is just a linear series or linear system of such objects. So something very geometric again, and somehow in the line with classical questions. So, and delta semistability, let me just at least define it. So if you have a weighted filtration, of E, then I said you get the associated weighted filtration of E rho. So this runs, say, from 1 to t, and so I define Bj to be the dimension of V intersected with H naught of Fj tensor L. And then the slope of this, I just call it mu. So it's similar to what I had before. So now I have some j from 1 to some t. And I have beta j rank of fj times the dimension of v minus rank of E rho. So the dimension of A times this beta j. So, and then you get this, you get that EV is delta semi-stable. If for all weighted filtrations E bullet alpha bullet of E, this quantity I introduced before, plus delta times this mu, this kind of mu of is greater or equal than 0. And I just state the result. So I fix some positive integers, A, R, A, S, let's say to equal 1. So there exists a projective moduli space for pairs E, V with following ingredients. E is a vector bundle, and delta. Delta in Q, I will specify it, E is a vector bundle of rank R, and degree D on X. V is now, so I take just the tensor representation, A-fold tensor representation, and no twisting, line bundle. For delta semi-stable, so I should say, and delta has to verify some inequality like this. Okay, so under these assumptions, there exists a moduli space. So the representation is just A-fold tensor representation. I don't allow a twisting here. And so there is some constraint on the stability parameter. AE is here, sorry. Right. Okay. So I should, to conclude, mention that this does not formally include the case of coherent Higgs systems. This is treated by Edgar Castañeda, a PhD student of Brambilla Pass. So it seems to be finished, but I have not seen it yet. And I should also mention that there is some kind of Kobayashi-Hitchin correspondence, which in principle also covers these objects and gives some notion of semi-stability. This is work by Bradlow, Garcia, Prada, and Mundet Herrera. And my PhD student, Cesare Goretti, is checking what comes out of this. And it seems that we, in fact, get such a condition. Okay, so I stop here. Thank you very much.